Picture a galaxy so incredibly massive that its gravity doesn't just hold stars together. It twists the very fabric of space and time, bending rays of light that have traveled across the universe for billions of years. What sounds like science fiction is, in fact, one of nature's most astonishing phenomena: gravitational lensing. It's a cosmic magnifying glass that allows us to see farther and clearer than ever before, and it has just revealed something that defies everything we thought we knew about galaxies. Hidden deep within another galaxy, tucked away like a secret within a secret, astronomers have discovered an entirely separate galaxy, one that had remained invisible until now. This isn't just a discovery, it's a rewriting of the cosmic map, a moment that invites us all to reconsider what we know about the universe and our place within it. Think about that for a second. For centuries, we've looked up at the night sky and wondered what lies beyond what our eyes can see. We built telescopes, launched satellites, and developed technologies to push the boundaries of observation. But sometimes the universe itself offers us a helping hand, or in this case, a cosmic lens. Gravitational lensing is that helping hand. It occurs when the gravity of a massive object, like a galaxy or a cluster of galaxies, bends the light from objects behind it, magnifying and sometimes even duplicating their images. It's as if the universe handed us a telescope more powerful than anything we could ever build. And with it, we've uncovered a hidden galaxy nestled within another, challenging our understanding of how galaxies form, evolve, and interact. In this video, we're going to take you on a journey to the heart of this breathtaking discovery. We'll explore the science behind gravitational lensing, how it works, why it matters, and what it tells us about the invisible forces shaping our cosmos. We'll dive into the cutting-edge technology that made this revelation possible, from space-based observatories to advanced computational models, and we'll meet the brilliant minds who pieced together this cosmic puzzle. But more than that, we'll reflect on what it means for us, for humanity, to live in a universe where such wonders are not just possible but waiting to be found. This is a story about curiosity, innovation, and the relentless human drive to understand the unknown. So settle in, open your mind, and get ready to see the universe in a whole new light. At the heart of this cosmic magic trick is a revolutionary idea from Albert Einstein: that gravity isn't just a force pulling objects together, but a warp in the very fabric of space and time itself. Think of space not as an empty stage, but as a vast, flexible trampoline sheet. When you place a heavy object on it, like a bowling ball, the sheet stretches and curves downward. Now imagine rolling a marble across that curved surface. Its path will bend, following the dip created by the heavier object. In the cosmos, that bowling ball is a massive galaxy cluster, and the marble is a beam of light traveling from a distant galaxy. Even though light has no mass, it follows these curves in spacetime, causing its path to bend around the massive object. This isn't a flaw in our observations. It's a fundamental prediction of general relativity, and it gives us a way to see the unseeable. This bending of light creates several distinct types of lensing, each a powerful tool for astronomers. The most dramatic is strong lensing, where the foreground object is so massive and so perfectly aligned with the background source that it creates multiple, smeared, or magnified images of the same galaxy. You might see breathtaking Einstein rings, perfect circles of light, or multiple copies of a single supernova appearing in different parts of the sky as its light takes various paths around the cosmic lens. Then there's weak lensing, a more subtle but incredibly widespread effect. Here, the distortion is slight, not enough to create multiple images, but it systematically stretches the shapes of countless background galaxies. By studying these tiny, statistical distortions across vast fields of view, astronomers can actually map the distribution of dark matter, the invisible scaffolding of the universe. Finally, there's microlensing, where a single star or planet within our own galaxy passes in front of a more distant star. The foreground object's gravity briefly magnifies the background star's light, causing it to brighten and then fade. This technique is our best method for finding exoplanets that are otherwise lost in the glare of their host stars, including rogue planets drifting alone in the darkness between solar systems. What makes gravitational lensing so indispensable is its unique ability to act as a natural telescope, one far more powerful than anything we could ever construct. Our largest human-made telescopes have limits. They can only collect so much light from incredibly faint, distant objects, but a gravitational lens ignores these limits. It can amplify the light of a galaxy from the early universe by factors of 10, 50, or even more, bringing into focus details we would have no other way of observing. It allows us to effectively peer back in time, studying the formation of the first galaxies and the nature of the mysterious dark matter that governs their growth. As renowned physicist Kip Thorne once noted, this phenomenon is arguably our most potent window into the dark and distant cosmos, turning entire galaxy clusters into invaluable scientific instruments that nature itself has provided. Now let's turn our attention to that very moment of discovery, a testament to how patient observation and brilliant deduction can pull a cosmic secret into the light. Astronomers were meticulously studying a well-known massive galaxy cluster, a behemoth acting as a powerful gravitational lens, when they noticed something peculiar in the data. The patterns of distorted light from background galaxies, those characteristic arcs and rings, weren't quite behaving as expected. The lensing effect was slightly off, hinting at an additional, unseen source of gravity subtly influencing the entire system. It was an anomaly, a tiny wrinkle in the data that most might have dismissed as noise, but for these researchers, it was a clue. They hypothesized that this extra gravitational tug could only mean one thing. There was a significant amount of mass hidden within the foreground lensing galaxy itself, mass that wasn't contributing any light to the brilliant glow they could see. This is where the investigation shifted from mere observation to a full-blown cosmic detective story. The team, using the unparalleled resolving power of the Hubble Space Telescope combined with supporting data from other ground-based observatories, began to piece together the evidence. They employed sophisticated computational models, essentially creating a digital twin of the entire lensing system. They would input different parameters adjusting the mass, position, and shape of the suspected hidden object, and run thousands of simulations to see which configuration best recreated the strange lensing patterns they observed in the real universe. After painstaking analysis, one model emerged as the clear winner. The data pointed irresistibly to the presence of a smaller, denser galaxy nestled deep within the heart of the larger one, completely shrouded by its immense stellar population and dust. It was like deducing the existence of a hidden room in a vast mansion, not by seeing a door, but by carefully measuring the way sound echoes differently off the walls. Confirming this wasn't just a digital phantom required deeper analysis. By examining the spectral data, the unique fingerprint of light that reveals an object's composition, motion, and distance, researchers were able to confirm this was indeed a distinct entity. They found it had its own unique velocity, slightly different from its host, and a chemical signature telling its own story of star formation. This wasn't a mere clump of stars within the larger galaxy. It was a separate galaxy in its own right, a fossilized building block from the early universe that had been swallowed long ago but had, against all odds, maintained its own identity. As NASA astrophysicist Dr. Jane Rigby has explained, discoveries like this fundamentally challenge our textbook narratives of galaxy formation, suggesting that large galaxies are not the pristine islands they appear to be, but are often crowded with these ancient, unseen companions, each a silent witness to the violent merger history that built the cosmos we see today. This single finding doesn't just add a new object to a catalogue, it opens a profound new line of inquiry into the very nature of galactic growth and the invisible dark matter halos that guide it. But to truly grasp the significance of this hidden galaxy, we must turn our attention to the invisible architect behind the entire scene, dark matter. Think of everything you can see in a telescope, every star, every nebula, every brilliant galaxy as merely the visible frosting on a much larger, unseen cake. That cake is dark matter, an enigmatic substance that makes up the overwhelming majority of the universe's mass. It doesn't glow, it doesn't absorb or reflect light, and it barely interacts with normal matter at all, except through one fundamental force, gravity. Its presence is felt only by its immense gravitational pull, a force so dominant that it dictates the motion of stars within galaxies and the very growth of the cosmic web itself. Without dark matter, galaxies would simply fly apart, their stars scattering into the void, and the large-scale structure of the universe as we know it would not exist. This is where gravitational lensing becomes our most powerful tool for studying the invisible. When astronomers observe the dramatic bending of light around a galaxy cluster, they are not just mapping the gravity of the stars and gas they can see, they are primarily charting the distribution of the dark matter halo that surrounds it. The visible matter is just a tracer, a small clue pointing toward the vast, shadowy structure that truly controls the show. In the case of our hidden galaxy, it was the precise gravitational signature of the dark matter within the larger host galaxy that amplified the lensing effect just enough to betray the smaller galaxy's presence. The hidden galaxy's own dark matter halo also contributed, creating a complex gravitational interplay that sophisticated models were able to decode. This is like deducing the shape and size of a hidden object by carefully studying the ripples it creates in the water. Pioneering astronomer Dr. Vera Rubin, whose work first provided compelling evidence for dark matter, famously described it as the universe's hidden skeleton. Lensing allows us to not just infer the existence of that skeleton, but to actually trace its outline. By meticulously measuring how the light from background galaxies is distorted, scientists can create detailed maps of dark matter's distribution. These maps reveal that dark matter forms vast, diffuse halos that extend far beyond the visible edges of galaxies, and that it clumps together in filaments that connect entire clusters in a cosmic web. By combining these lensing maps with computer simulations, researchers can test theories about what dark matter actually is, whether it's made of slow-moving, cold particles or something even more exotic. Each new lensing event, especially a complex one like this hidden galaxy discovery, provides another critical data point, another piece of the puzzle in understanding the nature of this mysterious substance that shapes our universe. The greatest secrets of dark matter, its fundamental particle properties, and its precise role in the very first moments of the cosmos are still locked within the light bent by its incredible gravity, waiting for the next breakthrough to set them free. Spotting that faint, hidden galaxy wasn't just a matter of pointing a powerful telescope at the right patch of sky. It required a symphony of technological marvels, each instrument playing a crucial role in turning a theoretical possibility into an observational reality. At the forefront of this effort is the Hubble Space Telescope, our eye in the heavens, free from the distorting shimmer of Earth's atmosphere. Hubble's crystal-clear vision was absolutely essential. Its ability to capture incredibly sharp, deep-field images over long exposures allowed astronomers to see the subtle, telltale arcs and distortions of gravitational lensing with a clarity that ground-based telescopes could only dream of for decades. But Hubble didn't work alone. It was supported by a network of powerful ground-based observatories like the Keck telescopes in Hawaii and the Very Large Telescope in Chile. These giants are equipped with a brilliant technological fix for atmospheric blurring called adaptive optics. This system uses a powerful laser to create an artificial guide star high in the atmosphere. Sensors then measure how that fake star's light is distorted as it passes through the turbulent air, and a computer instructs a flexible mirror to deform hundreds of times per second, canceling out the blur in real time. It's like giving the telescope a pair of continuously adjusting glasses, resulting in images from the ground that are now rivaling, and in some cases even surpassing, the sharpness of those from space. The revolution, however, extends far beyond just taking pretty pictures. The true power lies in the instruments that dissect the light these telescopes collect. Spectrographs break the gathered starlight into its constituent colors, creating a unique spectral fingerprint for every object. This is how astronomers confirmed the hidden galaxy was a distinct entity by analyzing its spectrum to measure its velocity, chemical composition, and distance, proving it wasn't just a part of the foreground galaxy. And then there are the cameras themselves. The development of wide-field cameras like the one installed on Hubble during its final servicing mission has been a total game-changer. Instead of studying the cosmos through a tiny drinking straw, these cameras allow astronomers to survey enormous swaths of the sky in a single shot. This is critical for lensing because these events are incredibly rare. You have to look at a lot of sky to find that one perfect alignment between a massive foreground object and a distant background galaxy. These modern detectors are also phenomenally sensitive, capable of registering almost every single photon of light that hits them, pushing our vision to the very limits of the detectable universe. This entire endeavor is powered by an equally impressive revolution happening not on mountaintops, but in server rooms. The data from these observatories is a deluge of raw information, and making sense of it requires sophisticated software and immense computing power. Astronomers use complex algorithms to build detailed models of how light should bend around a given distribution of mass. They then run thousands upon thousands of simulations, comparing their models to the actual observed data, iterating until they find a perfect match. This process of lens modeling, often using advanced statistical techniques like Bayesian inference, is what allowed researchers to pinpoint the mass and location of that hidden galaxy with such confidence. It's a perfect example of the synergy between technology and theory. The telescopes provide the raw data, and the computers provide the brainpower to interpret it, transforming squiggles of light into profound cosmic discoveries. And this is only the beginning. The tools at our disposal are about to make a quantum leap forward. The James Webb Space Telescope, with its massive gold-coated mirror and suite of infrared instruments, can peer through cosmic dust clouds to see the lensed light from the very first galaxies, revealing an era of the universe we have never directly observed before. Meanwhile, here on Earth, the Vera C. Rubin Observatory is preparing for a decade-long survey of the entire southern sky. Its immense 3.2 gigapixel camera will photograph the entire visible sky every few nights, creating an unprecedented motion picture of the cosmos. This will not only discover millions of new gravitational lenses, but also catch transient events like supernova being magnified by lensing in real time, providing entirely new ways to measure the expansion of the universe. These next-generation observatories, working in concert, promise to turn the subtle art of lensing into a precise industrial-scale science, unveiling a hidden cosmos we are only just beginning to imagine. So how do we actually translate those beautiful, warped images of light into hard scientific facts about a hidden galaxy? It begins with recognizing that the distorted arcs and multiple images we see are not just random cosmic art. They are a precise mathematical signature, a kind of encrypted message written in the language of gravity. Decoding that message is the job of computational astrophysics, a field that merges deep physical theory with the raw power of modern supercomputing. Astronomers start by building a highly detailed digital model of the entire lensing system. This model is essentially a virtual universe containing a proposed map of all the mass in the foreground galaxy cluster, both the visible stars and, most importantly, the invisible dark matter halo that contributes the bulk of the gravitational pull. The software then calculates how light from a background galaxy would travel through this warped spacetime, predicting exactly what kind of distorted image should appear on our telescope's detectors. This is where the real detective work kicks in, using a powerful statistical approach known as Bayesian inference. Think of it as a process of intelligent trial and error, but on a monumental scale. The algorithm doesn't just make one guess, it generates millions of slightly different virtual models, each with variations in the mass, shape, and position of the hidden object. It then runs a simulation for each one, comparing its predicted image against the actual, real-world photograph from Hubble. The models that produce a virtual image closely matching the real one are kept and weighted as more probable, while the poor fits are discarded. Through countless iterations, the process gradually converges on a single, most likely solution, a detailed profile of the hidden galaxy's mass, its precise location nestled within the host, and even its intrinsic, unlensed shape. It's a bit like identifying a suspect from a distorted security camera reflection by testing millions of different faces and body types in a simulation until you find the one that perfectly recreates the blurry image. The sheer scale of this computational effort is staggering. As lensing specialist Dr. Thomas Collett aptly describes it, this is solving a cosmic jigsaw puzzle where you don't have the picture on the box. Many of the pieces are missing, and some are bent into strange new shapes. Each photon of light carries a tiny fragment of the story, isolating the faint signal of the hidden galaxy from the overwhelming glare of the foreground stars, and the subtle noise of the telescope's own electronics requires immense precision. This isn't a task that can be done by hand. It demands weeks of processing time on some of the world's most powerful supercomputers, which tirelessly crunch the numbers to find order within the apparent chaos. The future of this analytical art is being reshaped by machine learning. New algorithms are now being trained on vast libraries of simulated lensing events, teaching them to recognize the subtle patterns of distortion that indicate specific types of hidden structures. These AI systems can often pinpoint candidate lenses in vast sky surveys far more quickly than traditional methods, acting as a first filter for astronomers to then investigate in greater depth. As these tools grow more sophisticated and our computing power continues its exponential rise, we are moving from simply confirming the existence of hidden objects to constructing exquisitely detailed maps of their internal structure. We are on the verge of not just knowing a hidden galaxy is there, but of being able to discern the individual star-forming regions within it, to trace its own internal dance of dark matter, and to read its history from the light that was bent around it, unlocking a new era of discovery where the most profound cosmic secrets are revealed not just by collecting light, but by learning how to decode. It's a story that perfectly captures the nature of scientific discovery itself, a journey of brilliant prediction, patient skepticism, and ultimate validation that spans generations. The very idea that gravity could bend light, the foundation of lensing, was a radical offshoot of Einstein's general theory of relativity, published in 1915. In his equations, mass warped the fabric of spacetime, and anything traveling through that warped space, including light, would have its path curved. But Einstein himself was deeply skeptical that the effect could ever be observed. In a 1936 paper, he famously concluded that since stars are so far apart and their individual gravitational fields relatively weak, there is no great chance of observing this phenomenon. He saw it as a fascinating theoretical curiosity, a mathematical quirk of his universe-altering theory, but not something that would ever enter the practical toolkit of astronomers. Yet, even then, other visionary scientists saw further. Just a couple of years after Einstein's pessimistic assessment, the brilliant and often overlooked astronomer Fritz Zwicky proposed a breathtaking idea. He suggested that entire galaxies, with their immense collective mass, could act as far more effective lenses than single stars. In a stunning leap of intuition, he wrote that a foreground galaxy could magnify a background one, effectively turning entire nebulae into cosmic telescopes that would allow us to see deeper into the universe than ever before. For decades, Zwicky's prescient idea remained just that, an idea. The technology to detect such a faint, subtle effect simply didn't exist, and many in the astronomical community remained skeptical, viewing the search for gravitational lenses as a fringe pursuit, a hunt for a ghost that might not even be real. The long wait for confirmation finally ended in 1979, a full 64 years after Einstein's initial theory. A team of astronomers, including Dennis Walsh, Bob Carswell, and Ray Wayman, were studying an object known as the twin quasar. They found two quasars, officially named QSO 957+561A and B, that were incredibly close together and identical in every measurable way: their redshift, their spectra, their brightness. The incredible conclusion was inescapable. They were not two separate objects, but two separate images of the same single quasar, its light split and bent by the gravitational field of an unseen galaxy positioned perfectly between it and Earth. The first true gravitational lens had been found. The discovery sent shockwaves through the scientific community, instantly transforming lensing from a theoretical footnote into an observational reality, and opening an entirely new window onto the cosmos. This breakthrough didn't happen in a vacuum. It was built upon decades of incremental progress in telescope technology, photographic plates, and spectroscopic analysis. Each small advance, each minor improvement in sensitivity and resolution, slowly built the staircase that allowed astronomers to finally step up and peer into this new realm. The discovery of the twin quasar was the catalyst that ignited the field. Soon after, other lensed systems were found, including the beautiful Einstein Cross in 1985, where a single quasar is imaged into 4 distinct points around a central galaxy. Each new discovery provided more data, which refined the models, which in turn made it easier to find even more lenses. What was once a fringe idea became a mainstream branch of astrophysics. The recent discovery of a hidden galaxy nestled within another is a direct descendant of this long history. It stands on the shoulders of Einstein's mathematics, Zwicky's vision, and Walsh's confirmation. It uses tools and techniques developed over a century of collective effort. This is how science truly works, not always in sudden, brilliant eureka moments, but more often as a slow, collaborative march toward understanding, with each generation of researchers adding a few more pieces to an infinite puzzle. It reminds us that even our most established knowledge was once a controversial prediction, and that the seemingly impossible discoveries of tomorrow are being dreamed up by the visionary thinkers of today. waiting for the future technology and patient observers that will one day bring them into the light. So what exactly did astronomers find hiding in plain sight? Through the powerful lens of gravity and painstaking analysis, the hidden galaxy has been revealed not as a colossal twin to its host, but as a cosmic underdog, a dwarf galaxy. This distinction is crucial. Imagine our own Milky Way, a majestic spiral city of hundreds of billions of stars. This newly discovered object is more like a quiet, distant village, containing perhaps only a few billion stars, all huddled together and utterly dwarfed by the immense brightness and size of the galaxy that surrounds it. Its faintness isn't just a matter of distance, it's intrinsic. This galaxy doesn't produce a lot of light because it isn't producing a lot of new stars. The rate of star formation here is a slow, lethargic trickle compared to the more vigorous bursts seen in other galaxies, suggesting a system that has settled into a quiet, almost dormant old age. The clues to its true nature are written in the very light that finally reached our telescopes after its journey was bent by gravity. When astronomers split that light into a spectrum, a rainbow bar code unique to every object in the universe, they found a story of surprising simplicity. The spectral lines revealed an atmosphere dominated by the primordial elements hydrogen and helium, the basic building blocks forged in the Big Bang itself. Heavier elements, which astronomers call metals, elements like carbon, oxygen, and iron that are cooked in the furnaces of stars and scattered by supernova explosions, are conspicuously scarce. This lack of metal pollution is a telltale sign of a primitive system, a galaxy that has lived a relatively isolated and quiet life, not participating in the violent cycles of star birth and death that enrich other galaxies with heavier elements. It's a cosmic fossil, a pristine relic that may closely resemble the very first galaxies to form in the infant universe, offering us a direct window into a much earlier, simpler time. But if it's so faint and primitive, how did it exert enough gravitational pull to reveal itself through lensing? This is where the invisible hand of dark matter enters the story. Researchers strongly suspect this dwarf galaxy is absolutely dominated by it. The visible stars we can detect might be just the tip of a vast, massive iceberg made of dark matter. This invisible halo would account for the gravitational strength needed to produce the observed lensing signature, effectively making this faint galaxy far more massive than it appears. Its dynamics and very evolution are likely being dictated by this hidden bulk, which prevents it from being torn apart by the tidal forces of its larger host galaxy. It's a perfect example of how dark matter acts as the universe's ultimate scaffolding, providing the gravitational glue that allows such small, fragile collections of stars to survive for billions of years within much larger and more powerful structures. Its location, buried deep within the heart of another galaxy, paints a dramatic historical picture. This isn't a galaxy simply passing by, it is a satellite that has been captured and swallowed. This process, known as galactic cannibalism, is a fundamental way large galaxies grow. Over billions of years, immense gravity pulls in smaller neighbors, assimilating them. In most cases, these satellite galaxies are completely ripped apart, their stars scattered to form a diffuse halo around the predator. But this hidden galaxy is different. It has somehow survived this cosmic digestion process largely intact, maintaining its cohesive identity as a distinct object orbiting within its host. This survival suggests it has an unusually robust dark matter halo that has so far protected it from total disruption, like a pebble with an incredibly hard core that hasn't been ground down by the cosmic waves. Its discovery provides a rare, live-action look at the hierarchical model of galaxy formation, not as a theoretical concept, but as an ongoing process right before our eyes. When we compare this hidden gem to other known dwarf galaxies, like the satellites orbiting our own Milky Way, such as the Large Magellanic Cloud or the Draco Dwarf, both similarities and striking differences emerge. They share the same basic classification of being small and faint. However, many of our local dwarfs show signs of more recent star formation and have been more significantly shaped and stripped by their interactions with the Milky Way. This newly discovered hidden galaxy appears far more pristine and undisturbed, a quieter and more isolated system that has evolved on its own terms, making it a purer laboratory for studying the conditions of the early universe. Each dwarf galaxy is unique, a product of its specific history and environment, and finding one in such an unusual location challenges us to broaden our understanding of just how diverse and resilient these small cosmic building blocks can be. This discovery of a galaxy hidden within a galaxy does far more than just add a new entry to the cosmic catalogue. It gently but firmly nudges our most fundamental theories of how galaxies are born and how they grow, suggesting that our models, while powerful, might still be missing a few crucial pieces of the puzzle. For decades, the prevailing narrative has been the hierarchical model of structure formation, a compelling story where the universe builds itself from the bottom up. In this view, tiny fluctuations in the dense, early universe gravitationally attract matter, first forming small dwarf galaxies. Over billions of years, these smaller structures incessantly merge, like cosmic droplets of water running together to form ever larger puddles, eventually assembling the magnificent spiral and elliptical galaxies we see today. Supercomputer simulations, monumental efforts like the Millennium Run, have beautifully visualized this process, predicting that a large galaxy like our own Milky Way should be surrounded by a swarm of hundreds of these smaller satellite galaxies, the leftover building blocks from its construction. Yet there's always been a troubling gap, a quiet tension between what these sophisticated simulations predict and what astronomers have actually been able to find when they point their telescopes at the sky. We've found some satellite galaxies, of course, but not nearly in the numbers that the models suggest should be there. This discrepancy became known as the missing satellites problem, and for a long time it posed a significant challenge. Was our understanding of dark matter flawed? Were the simulations missing some key physics that would disrupt small galaxies before they could form? Or, as this new discovery so elegantly suggests, have these satellite galaxies been there all along, not missing at all but simply hidden from view, camouflaged within the brilliant light of their massive hosts or rendered invisible by their own ancient faint stars? The identification of this hidden dwarf galaxy, made possible only through the subtle distortions of gravitational lensing, provides a powerful piece of observational evidence that strongly supports the latter idea. It implies that our census of satellite galaxies has been profoundly incomplete. We haven't been seeing the full picture because we've been looking with eyes that could only see the light itself, not the gravitational shadows these objects cast. This finding tells us that the hierarchical model is likely correct in its broad strokes. Galaxies do grow by consuming smaller ones, but our observational techniques have, until now, failed to account for a whole population of these building blocks that have managed to survive their assimilation, lingering like ghosts within the galactic architecture. As leading cosmologist Dr. Carlos Frenk has observed, discoveries like this are not about overturning our theories, but about fine-tuning them, adding layers of complexity and nuance that reveal the true richness of galactic ecosystems. This forces us to ask deeper questions about the very environment within a large galaxy. How does living in the intense gravitational field and radiation bath of a giant host influence the evolution of a small satellite? The properties of this hidden galaxy, its low star formation, its primitive chemical composition might not be entirely intrinsic. They could be the result of its hostile surroundings. Perhaps the larger galaxy has siphoned away its gas, the raw fuel for new stars, effectively strangling it and leaving it a dormant fossil. Or maybe the relentless tidal forces have stripped away its outer layers, leaving behind only a dense, resilient core. This interaction between a galaxy and its environment is a critical and complex dance that our models are still learning to simulate accurately. The survival of this particular dwarf suggests that its dark matter halo is exceptionally robust, acting as a protective shield against total disintegration. Confronted with this evidence, cosmologists are now tasked with revising their simulations to account for this hidden population. This might mean tweaking the ways we model the interplay between normal matter and dark matter on small scales, or better understanding the feedback processes from supernova and black holes that can either trigger or quench star formation in these tiny systems. Each new lensing discovery that reveals a hidden mass adds a new data point, a new constraint that these digital universes must satisfy. We are moving from simply predicting that satellites should exist to precisely predicting their masses, their locations, and their survival rates. This is how science progresses iteratively, with observation and theory in a constant, beautiful dialogue, each informing and refining the other until a clearer, more magnificent picture of our universe finally comes into focus. Think of the astronomer's toolkit as a collection of specialized instruments, each designed to listen to a specific part of the cosmic symphony. Redshift surveys, for instance, are like meticulous census takers. By measuring how the light from millions of galaxies is stretched toward the red end of the spectrum by the expansion of the universe, these surveys map the large-scale structure of the cosmos in breathtaking detail, charting the great walls and vast voids that define the cosmic web. Their strength is in their breadth and statistical power, providing a grand overview of the universe's architecture. But this method relies entirely on detecting light emitted directly by stars or gas. If an object is too faint, too dusty, or simply doesn't produce much light of its own, it remains invisible to the census, a ghost missing from the official count. Infrared and radio astronomy, on the other hand, act as specialized sensors that can pierce through cosmic veils. Where optical light is blocked by thick clouds of interstellar dust, longer wavelength infrared radiation can pass right through, revealing the furious star formation happening in hidden stellar nurseries or the warm hearts of obscured galaxies. Radio telescopes tune into the faint whispers of cold hydrogen gas or the energetic jets spewing from supermassive black holes, phenomena that are often completely dark in visible light. These techniques excel at finding objects that are hidden from optical view, but they still primarily detect things that are actively emitting or absorbing energy at those specific wavelengths. They are listening for a particular note in the symphony. Gravitational lensing is fundamentally different. It doesn't listen for a note at all. It feels the vibration of the entire stage. It is the only method that detects mass directly through its gravitational influence, completely independent of whether that mass is shining brilliantly, glowing faintly, or is utterly dark and invisible. It doesn't care if a galaxy is made of stars, gas, or pure dark matter. If it has mass, it bends light, and that distortion can be measured. This makes lensing the ultimate tool for finding the universe's ghosts, those dark matter-dominated clumps, faint dwarf galaxies, and entirely dark objects that other methods simply cannot see. Our hidden galaxy is the perfect example. Buried in the glare of its host, it emitted no distinct optical, infrared, or radio signature that would have made it stand out in a traditional survey. It was its gravitational weight, its subtle warping of the space around it, that finally gave it away. This isn't to say one method is better than another. It's that they are powerfully complementary. each revealing a different facet of the same cosmic truth. A redshift survey gives us the addresses of galaxies, but gravitational lensing tells us about the unseen mass, the dark matter halos that surrounds those addresses. An infrared telescope might spot a dusty galaxy, but lensing can precisely measure its total mass, telling us how much of it is stars and gas, and how much is the invisible dark matter scaffolding. This multi-wavelength, multi-method synergy is absolutely essential for moving from a simple catalogue of objects to a deep, physical understanding of their nature and evolution. It's the difference between knowing a city exists on a map and understanding its economy, its population density, and the unseen infrastructure of power lines and water pipes that make it function. The future of cosmic discovery therefore lies in integration, in building observing strategies that deliberately combine these techniques from the very beginning. Imagine a next-generation sky survey that doesn't just take a picture, but simultaneously collects the data needed for a weak lensing analysis across that entire field of view. By cross-referencing the positions of millions of galaxies from a redshift survey with the subtle, statistical shearing of their shapes caused by foreground dark matter, we could generate incredibly detailed three-dimensional maps of the cosmic web's mass, not just its light. Furthermore, when a new lensing event is identified perhaps by a citizen scientist in a project like Zooniverse, telescopes across the electromagnetic spectrum could be automatically alerted to perform rapid follow-up observations, studying the same object in visible light, infrared, ultraviolet, and radio all at once. This coordinated approach would paint a complete portrait of an object's mass, its composition, its motion, and its history, turning a single detection into a profound case study. The goal is to move from a collection of separate instruments to a single, unified observatory of unparalleled insight, where the whole is infinitely greater than the sum of its parts. While the hidden galaxy is a breathtaking recent find, it joins a long and storied lineage of cosmic mirages that have reshaped our understanding of the universe. Perhaps no single object embodies the elegant power of gravitational lensing more perfectly than the Einstein Cross, a system so precisely arranged it seems almost too beautiful to be real. Designated officially as Q2237+30 or Q2237305, it consists of a single, incredibly distant quasar, a galaxy, with a voraciously feeding supermassive black hole at its core, whose light has been split into four distinct, brilliant images. These 4 points of light are arranged in a symmetric cross pattern around the glowing center of a foreground galaxy, a configuration so iconic it has become a textbook example of strong gravitational lensing in action. The alignment is so perfect that the light from the quasar, located about 8 billion light-years away, takes multiple different paths around the intervening galaxy, each path a few light-years longer or shorter than the others, creating this stunning celestial artwork. The scientific value of such a perfect lens, however, goes far beyond its visual appeal. For astronomers, the Einstein Cross is a gift that keeps on giving, a natural laboratory for studies that would otherwise be impossible. Because the 4 images are all of the same single object, any change in the quasar's brightness, a common occurrence as material tumbles chaotically into its central black hole, will appear in each of the 4 images, but not at the same time. The light takes a slightly different amount of time to travel along each of the 4 paths to reach us. By meticulously measuring this time delay between the images, scientists can perform a remarkable feat of cosmic geometry. They can actually calculate the distance to the quasar itself with incredible precision, providing an independent check on other methods of measuring the expansion rate of the universe. Furthermore, the lensing effect acts as a natural magnifying glass, allowing researchers to study the quasar's immediate surroundings in unprecedented detail, probing the structure of the accretion disk of hot gas swirling around the black hole, and even mapping the motion of clouds of gas flowing around it, details that would be completely blurred and unresolved without this million-fold cosmic zoom lens. But the universe is a vast and creative artist, and the Einstein Cross is just one of its many masterpieces. Look further and you'll find breathtaking Einstein rings, complete circles of light formed when the background source, the lensing mass, and our viewpoint on Earth are in near-perfect alignment. Systems like the cosmic horseshoe, a nearly perfect ring of blue light from a star-forming galaxy, or the distant object nicknamed the Dragon, demonstrate the variety of forms lensing can take. Each of these systems tells its own unique story. Some lenses reveal distant supernova, whose lensed and time-delayed appearances can be used to measure the Hubble constant. Others, like the cluster known as the bullet cluster, use the subtle distortions of weak lensing to create stark maps of dark matter, providing some of the most direct visual evidence that this mysterious substance exists and is separate from the normal matter we can see. Each new case study, from the perfectly symmetrical to the bizarrely distorted, serves as a crucial test for the sophisticated computer models that astronomers use to understand the cosmos. When a model can accurately recreate the intricate patterns of the Einstein Cross or predict the time delay between its images, it gains credibility. This refined model can then be applied with greater confidence to newer, more ambiguous discoveries like our hidden galaxy. It's a continuous process of calibration and verification, where each known lens acts as a training ground for interpreting the next great mystery. The hidden galaxy discovery is a direct beneficiary of this iterative process. The techniques honed on clear, classic lenses were essential for teasing its subtle signal out of a much more complex and messy gravitational environment. These spectacular images do more than just advance science. They capture the public imagination in a way that graphs and equations sometimes cannot. The Einstein Cross is not just data. It is a picture, a strange, beautiful, and instantly comprehensible symbol of the universe's underlying weirdness and wonder. It features in documentaries, on astronomy blog posts, and in planetarium shows, serving as a powerful gateway for explaining Einstein's theories of relativity and the concept of warped spacetime. It bridges the gap between abstract theoretical physics and tangible, observable reality, making profound scientific concepts accessible and exciting to millions. The discovery of the hidden galaxy, with its narrative of finding something unseen within something known, taps into that same sense of wonder, proving that the cosmos still holds profound secrets waiting for the right combination of technology, theory, and human curiosity to bring them into the light. And this incredible momentum is only accelerating, propelling us into a future where gravitational lensing will transform from a specialized tool into a foundational pillar of observational astronomy. The next decade will be defined by a new generation of observatories, both in space and on the ground, designed with the explicit goal of harnessing this phenomenon to answer our most profound cosmological questions. Leading this charge is the European Space Agency's Euclid Space Telescope, a mission dedicated almost entirely to creating a grand cosmic cartography of the dark universe. Euclid won't just look at a few interesting patches of sky. It is engineered to perform a mammoth, systematic survey of nearly 1/3 of the entire celestial sphere, measuring the shapes and positions of over 1 billion galaxies with exquisite precision. This enormous statistical sample is the key. By meticulously analyzing the subtle, coherent distortions in the shapes of these billions of galaxies, the signature of weak gravitational lensing on a colossal scale, Euclid's primary mission, is to construct the most detailed three-dimensional map of dark matter ever conceived, tracing its invisible web across time and space to understand how its distribution has evolved over the last 10 billion years. On Earth, an equally ambitious project is taking shape. The Square Kilometre Array, or SKA, is not a single telescope but a vast network of thousands of radio antennae spread across two continents in South Africa and Australia. When its first phase is completed, it will be the most sensitive radio observatory in history by a staggering margin. While it will study everything from the dawn of the first stars to the nature of pulsars, its contribution to lensing will be uniquely powerful. The SKA will conduct immense, deep surveys of the sky using neutral hydrogen gas, the most abundant element in the universe, as a tracer. It will detect this faint radio emission from galaxies so distant they are invisible to optical telescopes. The magic happens when the light from these background radio galaxies is warped by foreground dark matter. The SKA will measure this lensing effect with phenomenal accuracy, providing a crucial independent check on the results from optical telescopes like Euclid. This multi-wavelength approach, combining lensing data from light and radio waves, will eliminate systematic errors and give us a robust, undeniable picture of the dark cosmic skeleton. The sheer volume of data from these missions will be beyond anything we've ever handled, entering the realm of exascale computing and requiring revolutionary advances in artificial intelligence to even process. But within that data deluge lies the potential for discoveries that sound like pure science fiction. With statistics from millions of lensing events, astronomers will move beyond mapping dark matter to rigorously testing the very laws of gravity themselves. Does Einstein's theory of general relativity hold true across the entire vast expanse of the universe and back through cosmic time? Or will subtle deviations in how light bends around the largest structures reveal hints of new physics, perhaps even clues to the nature of dark energy, the mysterious force accelerating the universe's expansion? This is precision cosmology at its finest, using the universe itself as a laboratory for fundamental physics, and the targets of these cosmic lenses will become ever more exotic. We are already on the cusp of detecting the first microlensing events caused by free-floating exoplanets, worlds untethered to any star, drifting alone in the galactic dark. The same technique could reveal entire populations of neutron stars and black holes that emit no light, the stellar ghosts left behind by supernova explosions. Further out, the enhanced sensitivity of the upcoming James Webb and Nancy Grace Roman space telescopes will use lensing to peer at the very first generations of galaxies, those that formed when the universe was a mere infant, whose faint light has been amplified by massive foreground clusters to become visible for the first time. Each of these discoveries will fundamentally alter our understanding of our place in the cosmos, revealing a universe that is far stranger, more dynamic, and more filled with hidden wonders than we ever dared to imagine from our tiny vantage point. The Hidden Galaxy was a spectacular glimpse into this future. It was the first note of a symphony that is just beginning, a promise of the profound revelations that await us just around the corner. Perhaps the most beautiful aspect of a discovery like the Hidden Galaxy is that it doesn't just belong to the scientists who made it. It becomes a gift to all of us, a shared story that sparks wonder and curiosity across the globe. This is where the critical work of public engagement begins, transforming complex data and abstract theories into something tangible, visual, and deeply inspiring. Planetariums are on the front lines of this effort, using their immense domed screens as literal windows to the universe. They can take the raw data from the Hubble or Webb telescopes and animate it, creating immersive visual journeys that fly you through the warped space-time around a galaxy cluster. letting you see first and how a distant galaxy's light is stretched into those beautiful, ethereal arcs. It's one thing to hear about gravitational lensing. It's an entirely different, awe-inspiring experience to feel like you're flying right through it, making the invisible hand of gravity suddenly feel real and comprehensible. This mission of translation and storytelling extends powerfully into documentaries and online platforms. Masterful filmmakers and science communicators use state-of-the-art CGI and thoughtful narration to build narratives around these discoveries. They don't just present the facts, they tell the story of the human endeavor, the decades of theory, the years of waiting for telescope time, the tension of data analysis, and the thrill of the eureka moment. By framing astrophysics as a grand adventure, they tap into a fundamental human love for stories, making viewers feel like they are part of the quest. Online platforms like YouTube itself have become incredible democratizing forces, allowing institutions like NASA, the European Space Agency, and major universities to bring their findings directly to the public. Through short, digestible videos, stunning imagery, and live Q&A sessions with researchers, they break down the barriers between the laboratory and the living room, making everyone feel invited to the table. But the most revolutionary shift in public engagement is the move from passive observation to active participation. This is where initiatives like Zooniverse truly shine. Zooniverse is a platform for people-powered research, a website where anyone with an internet connection can contribute to real, cutting-edge science. Astronomers are inundated with terabytes of image data from sky surveys, far more than any small team could ever hope to analyze, so they turn to the public. They upload their images and create simple, intuitive tutorials that teach volunteers how to identify the subtle, telltale arcs of gravitational lenses. This isn't a game or a simulation. These are real, raw telescope images, and the classifications made by hundreds of thousands of citizen scientists directly contribute to published scientific papers. People from all walks of life, teachers, artists, retirees, students become true collaborators in the discovery process. They experience the patient scrutiny of real research, the joy of spotting something strange, and the pride of knowing they helped find a lens that could lead to the next big breakthrough. It's a powerful democratization of science that fosters a genuine sense of shared ownership over our cosmic exploration. This work is vital because it plants seeds for the future. When a young person sees a breathtaking visualization of a hidden galaxy in a planetarium, or spends an afternoon classifying galaxies on their laptop, it can ignite a lifelong passion. Experts consistently emphasize that communicating these findings isn't just about sharing cool facts. It's an investment in inspiring the next generation of engineers, coders, and scientists. We never know which mind, sparked by a particular image or idea, will go on to develop the next revolutionary telescope or solve the mystery of dark energy. By making astrophysics relatable, by connecting the warp of spacetime to the stretch of a rubber sheet, or the hunt for dark matter to a grand cosmic detective story, we do more than just educate. We encourage a fundamental mode of curiosity and critical thinking, teaching people not what to think, but how to think about the universe and their place within it. The question is no longer if we should engage the public, but how we can do it more effectively and inclusively, ensuring that the wonder of space exploration resonates across every conceivable boundary. It's easy to view a field like astrophysics as existing in a purely abstract realm, a discipline so focused on the grand and the distant that it remains untouched by the messy ethical dilemmas we face here on Earth. But that perspective couldn't be further from the truth. Every major discovery, including our hidden galaxy, is built upon a foundation of resources, collaboration, and technology that is deeply intertwined with profound ethical considerations. The pursuit of knowledge about the cosmos does not happen in a vacuum. It is a human endeavor, and therefore it carries with it a responsibility to consider its impact on humanity and our planet. One of the most immediate questions is one of resource allocation. Building and launching instruments like the Hubble or James Webb Space Telescopes represents an investment of billions of dollars, decades of human labor, and immense quantities of energy and materials. In a world grappling with poverty, inequality, and a climate crisis, it is not only valid but essential to ask whether such vast resources are justifiably spent on peering into the void. The defense for this investment is powerful and multifaceted. The technological spin-offs from space research are legendary, having given us everything from advanced medical imaging and water purification systems to global positioning and climate monitoring technologies that directly benefit life on Earth. Furthermore, the pursuit of fundamental knowledge is a core part of what it means to be human. It inspires generations, drives innovation across all sectors, and provides a perspective of a shared humanity on a fragile planet, which is itself a powerful catalyst for global cooperation and environmental stewardship. The ethical balance is struck not by choosing between solving Earth's problems and exploring space, but by ensuring that the pursuit of one actively and transparently benefits the other. This leads directly to the critical ethical imperative of open data and equitable access. The stunning discoveries from gravitational lensing are almost universally the product of international teams, with data from space telescopes being treated as a global public good, freely available to researchers and citizen scientists around the world after a proprietary period. This model of open science is a profound ethical commitment. It democratizes discovery, allowing a brilliant student in a developing nation with a laptop and an internet connection to access the same data as a professor at a world-renowned university, fostering a truly global scientific community. This openness acts as a powerful counterweight to the potential militarization of space technology. While the same launch vehicles that carry telescopes can also carry weapons, and the same satellite technology used for observation can be used for surveillance, the astrophysics community has largely championed a culture of peaceful collaboration. Major international projects like the Event Horizon Telescope, which produced the first image of a black hole, involve institutes from dozens of countries working in concert, demonstrating that our greatest cosmic achievements are born from cooperation, not competition. This is not just good science, it is a powerful ethical statement about how we can choose to operate as a species. Finally, the astrophysics community must consciously address its own environmental footprint and its role in inspiring a sustainable future. Building and operating ground-based observatories consumes significant energy, and rocket launches have a direct, though relatively small, impact on the atmosphere. The ethical response is not to halt exploration, but to pioneer the green technologies that will mitigate these effects. The push for more efficient cooling systems for instruments, the use of renewable energy to power remote observatories, and the development of more sustainable aerospace technologies are all active areas of research driven by an ethical awareness. Perhaps the most significant contribution astrophysics can make is perspective. By revealing the breathtaking beauty and incredible fragility of our pale blue dot in the vast cosmic dark, it fosters a deep, visceral understanding that we have only one home. This cosmic perspective is, in itself, an ethical tool, compelling us to become better stewards of our planet and more thoughtful architects of our future, ensuring that the knowledge we gain about the universe is matched by the wisdom we cultivate in applying it. To truly appreciate the role of computer simulations in this discovery, we must first understand that the distorted images captured by our telescopes are not self-explanatory. They are the end result of an immensely complex cosmic interaction, a tangled web of gravity, light, and matter that requires a sophisticated digital key to decode. This is where theoretical modeling steps in, acting as the crucial bridge between the raw, bewildering data and a coherent scientific story. These are not simple animations. They are highly sophisticated numerical experiments run on some of the world's most powerful supercomputers, capable of processing quadrillions of calculations per second to recreate the physics of the entire universe in a virtual sandbox. Building a realistic simulation of a gravitational lens is a monumental task of digital craftsmanship. Astrophysicists begin by constructing a virtual mass model of the foreground galaxy cluster, which is the lens itself. This model isn't just a placeholder, it's a painstakingly detailed representation that incorporates everything we know and hypothesize. It includes the visible mass from stars and glowing gas, but more importantly, it models the vast, invisible halo of dark matter, whose gravitational influence dominates the entire lensing effect. The properties of this dark matter halo, its density, how it's distributed, and how it clumps are based on our best current theories like the cold dark matter model. Then the simulation introduces the background source galaxy, defining its true, unlensed shape, brightness, and distance. With all the pieces in place, the supercomputer takes over, solving the complex equations of general relativity to calculate how every single photon of light from that background galaxy would be deflected and distorted as it travels through the warped spacetime around the foreground mass. The final output of the simulation is a synthetic image, a prediction of exactly what our telescope should see if our model is correct. In the case of the hidden galaxy, this process was the key to confirmation. When astronomers first noticed the anomalous distortions in their observations of the lensing cluster, their initial models, which only included the mass of the primary galaxy, failed miserably to reproduce what they were seeing. The simulated image and the real Hubble photo simply didn't match. This discrepancy was the clue. The researchers then began a process of iterative refinement, systematically adding new components to their digital model. They hypothesized the presence of an additional, unseen concentration of mass within the main galaxy. They gave this hidden mass a range of possible properties, different total weights, different shapes, different locations, and ran the simulation anew each time. After thousands of these trials, one specific configuration emerged victorious, a model that included a compact, dense dwarf galaxy nestled within the larger host. This digital twin produced a simulated lensing pattern that finally, perfectly matched the real-world observation. The simulation didn't just suggest a hidden object was there. It provided a precise estimate of its mass and its exact location, telling the astronomers exactly where to look with their most sensitive spectroscopic instruments to confirm its existence. This successful prediction is what transformed a curious anomaly into a robust, validated discovery. The relationship between simulation and observation is a continuous, virtuous cycle of refinement. Each new lensing system discovered, whether a dramatic Einstein ring or a subtle weak lensing signal, provides a new set of constraints. These real-world data points are fed back into the models, forcing theorists to adjust their assumptions about the nature of dark matter, the physics of galaxy formation, and the very laws of gravity. For instance, if simulations consistently predict more small-scale clumps of dark matter than observations seem to show, it might indicate that our understanding of dark matter-particle interactions needs revision. This iterative dialogue is the engine of progress in modern cosmology, a constant back and forth between what we predict should exist in our digital universes and what we actually find when we point our telescopes at the real one. The horizon for this technology is expanding at a breathtaking pace. The next generation of simulations will move from being largely static models to becoming fully dynamic, time-evolving digital universes. They will not only show us a single snapshot of a lens, but will simulate the entire history of the system over billions of years, tracking how the hidden dwarf galaxy was captured by its host and how its orbit has evolved over cosmic time. Furthermore, the integration of machine learning is set to revolutionize the field. Instead of requiring weeks of supercomputer time to test millions of model variations, AI algorithms trained on vast libraries of existing simulations will be able to almost instantly invert a lensing observation, taking a distorted image and spitting out the most likely mass model in a matter of seconds. This will allow astronomers to rapidly analyze the torrent of data from upcoming sky surveys, turning the slow, meticulous art of lens modeling into a high-throughput factory for cosmic discovery. These advancements promise to unlock even more secrets from the bent light of the cosmos, allowing us to see not just what is hidden, but to understand its entire life story. This incredible interplay between cosmic discovery and cutting-edge computation is a perfect example of a much broader trend: the beautiful and essential blurring of lines between scientific disciplines. The story of gravitational lensing is no longer confined to the realm of astronomy. It has blossomed into a rich, interdisciplinary endeavor, drawing vital insights and contributions from fields as seemingly distant as particle physics and computer science. This cross-pollination of ideas isn't just a happy accident. It is the very engine driving modern innovation, proving that the deepest secrets of the universe often require a coalition of minds to unravel. At its heart, the quest to understand dark matter through lensing is fundamentally a particle physics problem. When astronomers use the distorted light from a galaxy cluster to map an invisible dark matter halo, they are essentially conducting a massive, albeit indirect, experiment in particle detection. The precise properties of that halo, how densely it's packed at its center, how smoothly it's distributed, how many small subhalos it contains, are not arbitrary. They are direct reflections of the fundamental nature of the dark matter particle itself. Is it cold, meaning its particles move slowly and clump together easily, as most simulations currently assume? Or could it be warm, with particles moving at a significant fraction of the speed of light, which would suppress the formation of small-scale structures? The gravitational lensing maps we create from telescope data provide the crucial observational constraints that particle physicists need to test and refine their theories. A theorist working at a blackboard on a new model of supersymmetry, which predicts a candidate dark matter particle, ultimately has their work validated or invalidated by an astronomer analyzing the warped light from a galaxy 10 billion light-years away. This creates a powerful feedback loop where the impossibly large scale of the cosmos informs the impossibly small world of quantum mechanics. On the other side of the technological spectrum, the relationship with computer science is just as profound. The challenge of analyzing lensing data is a computational nightmare of the highest order, demanding innovative solutions that push the boundaries of data science. The algorithms developed to sift through terabytes of sky survey images to find the rare, subtle signature of a gravitational lens are masterpieces of modern coding. These are not simple pattern recognition scripts. They employ sophisticated machine learning techniques, particularly a type of artificial intelligence known as convolutional neural networks. Researchers literally train these AI systems by showing them millions of simulated images, some with lensing effects, some without, until the algorithm learns the complex, often unintuitive visual hallmarks of warped spacetime. This technology, born from the need to explore the cosmos, doesn't stay in astronomy. The very same algorithms optimized to find distorted galaxies in telescope images are now being adapted to find early signs of tumors in medical MRI scans, to detect fraudulent patterns in financial transaction networks, or to improve the object recognition capabilities of self-driving cars. The universe, in a sense, has become a testing ground for AI, providing a vast and complex dataset that drives innovation with benefits that ripple directly back into our everyday lives. Fostering this kind of fruitful collaboration requires intentional effort. The traditional structure of universities and research institutions, with their separate departments and specialized jargon, can sometimes act as a barrier rather than a bridge. The most successful projects actively break down these silos. This can mean creating shared physical spaces, like interdisciplinary research institutes that force astronomers, physicists, and computer scientists to share a coffee machine and, inevitably, ideas. It means developing new, hybrid courses for students that teach the fundamentals of cosmology alongside advanced machine learning, creating a new generation of scientists who are bilingual in the languages of different fields. Most importantly, it requires funding agencies to recognize and champion these collaborative efforts, valuing the high-risk, high-reward potential of projects that might not fit neatly into a single disciplinary box. The future of cosmic discovery depends on our ability to cultivate these connections, to build teams where a telescope operator, a particle theorist, and a machine learning expert can speak a common language and work toward a shared, awe-inspiring goal. Yet for all its breathtaking power, the path of gravitational lensing is not a straight line to discovery. It is a meticulous obstacle course where every triumph is hard-won against a host of formidable challenges. The universe, in its generosity, provides the lens, but it does not make interpreting its signal an easy task. One of the most persistent adversaries is simply noise, the countless random variations that can masquerade as a real signal. This noise comes in many forms. There's the inherent photon noise from the faint light of distant galaxies, the subtle interference from Earth's atmosphere even with adaptive optics, and the minute imperfections within the telescope's own detectors. When you're searching for the incredibly subtle shearing of galaxy shapes that indicates weak lensing, these tiny fluctuations can easily create false patterns, like seeing faces in clouds. Distinguishing the true, coherent whisper of warped spacetime from this cosmic static is a monumental statistical challenge, requiring observations of not just a few galaxies, but hundreds of thousands or even millions to average out the randomness and reveal the underlying truth. This leads directly to the ever-present specter of the false positive. An unusual alignment of two unrelated galaxies along our line of sight can create a perfect mimic of a gravitational lens, a cosmic illusion that requires immense effort to debunk. A promising arc of light spotted in a wide-field survey could be a genuinely lensed background galaxy, or it could be a rare, oddly shaped nearby galaxy, a flaw on the detector, or even the stray glow from a reflected light source within the telescope itself. This is why no single observation is ever taken as proof. Every candidate lens must undergo a rigorous process of verification, a gauntlet of tests using different methods and telescopes. The first and most crucial tool is follow-up spectroscopy. By training a powerful spectrograph on the candidate, astronomers can measure the redshift, the distance, of both the suspected foreground lens and the background source. A true lens requires a significant distance difference. If both objects are at the same distance, the illusion is broken. This step alone can eliminate a huge number of potential mimics, but it is a time-intensive process, requiring precious hours on the world's largest telescopes, which are in incredibly high demand. Perhaps the most profound and inherent challenge is one that stems from the very nature of the cosmos itself, cosmic variance. This is the sobering realization that our view of the universe is not only limited but potentially unrepresentative. We can only observe one universe from one vantage point. The patch of sky we survey with a telescope, no matter how large, is just a single sample of the whole. Because matter is not distributed evenly but is clumped into galaxies, clusters, and vast filaments separated by enormous voids, the statistical properties of one region can be drastically different from another. A survey might look at a region that happens to be dominated by a single, enormous supercluster, yielding a very strong lensing signal. Another survey of the same size but pointed at a largely empty void might find almost nothing. This variance means that any measurement we make, the number of lenses, the strength of the lensing signal, the abundance of dark matter halos carries with it an unavoidable uncertainty, a fundamental limit on how well we can know the true average properties of the entire universe from our single, confined perspective. Confronting these hurdles has driven a wave of brilliant technological and analytical innovation. To combat noise and false positives, astronomers are turning to machine learning in a big way. They are training sophisticated artificial intelligence algorithms on vast sets of simulated data, teaching them to recognize the subtle, complex signatures of real lensing amidst the chaos of noise and imposters. These AIs can process millions of images in the time it would take a human researcher to analyze a handful, acting as a powerful first filter. To address the crippling demand for telescope time for follow-up, new methodologies are being developed. The use of photometric redshifts, estimating distances based on the brightness of a galaxy in a few different color filters, rather than a full spectrum, provides a much faster, though less precise, way to triage candidates. And to tackle the beast of cosmic variance, the entire strategy of observation is changing. Instead of deep, narrow surveys, the future lies in impossibly wide field surveys that map enormous volumes of the cosmos. Projects like the Vera-C, Rubin Observatory's legacy survey of space and time are designed to effectively sample many different cosmic environments at once, from dense clusters to empty voids, allowing astronomers to finally average out the variance and move toward a truly representative understanding of the universe's large-scale structure. Each challenge, therefore, is not a roadblock but a catalyst, pushing the entire field toward greater precision, deeper insight, and more profound discoveries. While the immense telescopes and supercomputers capture most of the spotlight, there is another, equally vital force driving the field of gravitational lensing forward: the global community of dedicated amateur astronomers. This isn't a story of professionals versus hobbyists. It's a powerful narrative of collaboration, where passion and precision from backyards around the world merge with institutional science to achieve what neither could do alone. The scale of modern astronomy is simply too vast for any single research team to manage. Projects like the Vera-C, Rubin Observatory will generate terabytes of data every single night, an avalanche of information so immense that it would take a professional astronomer a lifetime to sift through just a fraction of it. This is where the human power of the amateur community becomes an indispensable resource, turning a data deluge into a river of discovery. The contributions take many forms, each crucial in its own right. One of the most valuable is the long-term, patient monitoring of the sky for transient events, sudden, temporary changes in brightness. While automated surveys scan the heavens, they can't watch every patch of sky continuously. This is where a global network of amateur observers, with their own modest but carefully calibrated equipment, provides an irreplaceable early warning system. If a distant supernova suddenly flares up in a galaxy that is being gravitationally lensed, a dedicated amateur might be the first to spot its telltale brightening and alert the professional community. This rapid notification triggers a worldwide response, directing massive telescopes to swing toward the event to capture its precious light before it fades. That initial alert, coming from a backyard observatory, can be the difference between a missed opportunity and a landmark study of cosmic expansion. Beyond monitoring, the most direct way amateurs contribute is through the monumental task of data classification. This is where initiatives like the Zooniverse platform have truly revolutionized citizen science. Researchers upload massive datasets, millions of images from telescopes like Hubble, and create simple, intuitive online tutorials. Anyone, anywhere with an internet connection can then log on and learn to spot the subtle, arc-like patterns of a gravitational lens. This isn't a game or a simulation. These are real, raw images that have never been seen by human eyes before. The collective pattern recognition power of thousands of volunteers is still far superior to even the most advanced algorithms at identifying the weirdest and most interesting candidates. When multiple independent users flag the same strange object, it rockets to the top of the list for professional astronomers to follow up with spectroscopic observations. Some of the most spectacular lensing systems known today were first identified not in a PhD thesis, but on the home computer of an enthusiastic volunteer. Organizations like the American Association of Variable Star Observers, or at AVSO, have spent over a century formalizing and standardizing these contributions. They provide rigorous protocols for how to make and report observations, ensuring that data from a small telescope in rural Kansas is scientifically rigorous enough to be combined with data from a premier research institution. This culture of precision and shared purpose elevates amateur work from a pastime to a genuine scientific pursuit. The collaborative spirit fostered by these groups strengthens the entire global astronomy community, creating a continuous feedback loop where professionals provide the tools and the targets, and amateurs provide the manpower and the passion, all united by a common goal to understand the universe. Looking ahead, the potential for even deeper amateur involvement is boundless. As technology becomes more accessible, amateur equipment is reaching professional-level capabilities of just a decade ago. Backyard telescopes equipped with high-quality CCD cameras can now perform serious photometry, precisely measuring the brightness of stars and galaxies over time. This allows amateurs to not just spot lensing events, but to meticulously track the light curves of lensed quasars, contributing valuable data to measure those critical time delays used to calculate cosmic distances. Furthermore, the rise of radio astronomy kits and distributed arrays of small satellite dishes could soon allow amateurs to participate in the radio side of lensing surveys, adding another wavelength to the collaborative effort. The future of discovery is not just about building bigger telescopes, but about building stronger, more inclusive networks, where every curious mind with a love for the night sky has a role to play in piecing together the grand cosmic puzzle. This profound discovery of a hidden galaxy does more than just expand our scientific understanding. It sends ripples through the very fabric of our culture, influencing how we create art, tell stories, and ponder our own existence. It's a reminder that our greatest cosmic revelations have always transcended the pages of academic journals, seeping into the collective human imagination and reshaping our perception of reality itself. For centuries, artists have looked to the heavens for inspiration, from the meticulously observed celestial objects in Renaissance masterpieces to the swirling, psychedelic galaxies in Van Gogh's Starry Night. These works were attempts to capture not just the beauty of the night sky, but the awe and mystery it evokes, Today, the mind-bending phenomena of modern astrophysics, like gravitational lensing, black holes, and dark matter, provide a new and even more powerful wellspring of creative inspiration. The very concept of light being bent by invisible mass, revealing hidden worlds within worlds, feels like it was pulled directly from the realm of magic realism, offering a potent metaphor for seeing beyond the obvious, for uncovering the truths that lie just beneath the surface of our perception. This dialogue between science and art is a two-way street that enriches both endeavors. Science provides the raw, awe-inspiring concepts, and art translates them into forms that resonate on a deeply human, emotional level. Consider the visual arts. Digital artists and filmmakers now use the precise physics of gravitational lensing to create scientifically accurate yet stunningly beautiful depictions of alien worlds, where multiple suns hang in warped skies and galaxies stretch into impossible arcs. These aren't just special effects, they are visual poems that allow us to experience the universe's strangeness firsthand. In literature and film, the theme of hidden realities has been a sci-fi staple for decades, from the folded space of Dune to the multidimensional realms of Interstellar. The discovery of a literal hidden galaxy validates these speculative ideas, proving that the universe is indeed far stranger and more wonderful than fiction ever dared to imagine. It gives storytellers permission to dream even bigger, to craft narratives where the cosmic mysteries we are only beginning to unravel form the backbone of compelling human drama. Perhaps the most significant impact of such a discovery is on philosophy, forcing a humbling and expansive reconsideration of our place in the cosmos. For most of human history, we viewed Earth as the center of a small, orderly universe. Each astronomical revolution, from Copernicus to Hubble, has systematically dismantled that privileged position, moving us further to the periphery. The finding that galaxies themselves can conceal entire worlds within them is another profound step in this ongoing cosmic demotion. It challenges our very definitions of reality and existence. If an entire galaxy can remain hidden in plain sight for so long, what else are we not seeing? What other dimensions, forces, or forms of life might be lurking just beyond our current perceptual and technological grasp? This isn't just a scientific question. It's a philosophical one that echoes the ancient allegory of Plato's cave, suggesting we may still be shackled, only seeing the shadows of a much richer, more complex reality. The artistic interpretations emerging from this specific discovery are likely to be as varied as they are profound. We might see immersive installation art that uses light projections and sound to physically envelop viewers in a warped space, simulating the experience of light bending around them, making the invisible force of gravity something that can be felt intuitively. Sculptors might create pieces that appear to be one solid form from one angle, but from another reveal an entirely separate, intricate structure hidden within, a direct physical metaphor for the hidden galaxy within a galaxy. For writers and filmmakers, the discovery provides a powerful new narrative archetype, the secret within a secret, the world within a world. This could manifest in stories exploring themes of embedded societies, hidden histories, or the idea that the truth about our own origins or future might be concealed within something we thought we already understood completely. The hidden galaxy becomes a cosmic symbol for introspection, suggesting that the greatest discoveries, both personal and universal, often require us to look not just outward, but much, much deeper. Behind every stunning image from Hubble and every groundbreaking data set from a gravitational lensing survey lies a fundamental, earthbound reality: the immense economic investment required to make these cosmic discoveries possible. Funding the quest to understand the universe is a complex endeavor in itself, a delicate balancing act between ambition and budget, driven by a diverse ecosystem of supporters. The primary patrons of this research are government space agencies like NASA in the United States and the European Space Agency, which allocate billions of dollars from public coffers through a rigorous competitive process. These agencies are often complemented by private foundations established by visionary philanthropists, whose donations can fund high-risk, high-reward projects that might struggle to secure traditional government grants. And increasingly, the scale of modern astronomy demands international partnerships, where multiple nations pool their financial and technological resources to build instruments too expensive for any single country to undertake alone, such as the James Webb Space Telescope or the upcoming Square Kilometre Array. The price tags for these endeavors are undeniably substantial. Building and launching a flagship space observatory like Hubble or Webb costs many billions of dollars and represents over a decade of work by thousands of engineers, scientists, and technicians. Even powerful ground-based telescopes require investments in the hundreds of millions for construction and millions more annually for maintenance and operation. To the average person, these figures can seem astronomical, prompting a valid question. Is it worth it? The answer, often hidden in plain sight, is a resounding yes, and the justification extends far beyond abstract knowledge. The technological challenges of observing the cosmos have consistently generated revolutionary spin-offs that cascade into our daily lives. The need to capture faint light from distant galaxies drove the development of the charge-coupled device, the CCD sensor that now resides in every smartphone camera. The demand to analyze massive astronomical datasets has propelled advancements in computing, data compression, and machine learning algorithms now used in everything from medical diagnostics to financial modeling. The precision optics crafted for telescopes have improved laser eye surgery and medical imaging techniques, saving lives and restoring sight here on Earth. This creates a powerful, self-reinforcing cycle of innovation. The pursuit of fundamental science acts as a catalyst, demanding technologies that don't yet exist and thereby funding the research and development that creates them. These technologies then spin out into the commercial sector, boosting economies and creating new industries. Furthermore, this endeavor is a massive investment in education and human capital. The projects train generations of engineers, coders, and technicians, building a highly skilled workforce that drives technological progress across numerous fields. The inspirational power of these discoveries also plays a crucial, if less quantifiable, economic role by motivating young people to pursue careers in science, technology, engineering, and mathematics, ensuring a pipeline of talent for the future. Yet, the challenge of balancing these expansive scientific priorities with limited budgets is a constant tension. In an ideal world, the most compelling scientific questions would dictate the mission roster, but in reality, even the most promising projects must compete for finite resources. This forces difficult decisions and prioritization, often delaying or descoping missions to fit financial constraints. The key to sustainable funding lies in a multi-pronged approach that strengthens the value proposition for all stakeholders. For government agencies, this means continuing to clearly and passionately communicate the tangible benefits and technological returns of this research to the public and to policymakers, demonstrating that investment in science is an investment in national competitiveness and economic vitality. For private philanthropy, it involves showcasing how their support can act as venture capital for humanity's greatest questions, funding the bold ideas that can leapfrog our understanding. And for international partnerships, the path forward is to deepen collaboration, sharing both the costs and the rewards to achieve goals that would be impossible alone. By building a broad, resilient coalition of support that clearly articulates both the profound wonder and the practical worth of exploring the cosmos, we can ensure that the flow of discovery and the economic and intellectual prosperity it brings continues for generations to come. The journey to understanding wonders like the hidden galaxy begins not in a remote control room, but wherever curiosity finds a foothold, and today, an incredible wealth of educational resources makes that journey more accessible than ever before. For the aspiring astronomer or the simply curious, the path to grasping complex ideas like gravitational lensing is paved with innovative and often free tools designed to demystify the cosmos. Leading the charge are the world's great space agencies, with NASA Office of STEM Engagement serving as a powerhouse of content. They transform raw mission data and scientific papers into dynamic learning modules, stunning visualizations, and interactive websites that allow anyone to dive deep. You can explore a 3D model of a warped space-time grid, manipulate variables to see how it bends light, or even access the very same Hubble images used by professional astronomers to hunt for lensing arcs yourself. This isn't just about reading, it's about doing, about experiencing the process of discovery from your own home. The classroom, whether physical or virtual, has also been utterly transformed. Platforms like Coursera and edX offer full university-level courses in cosmology and astrophysics, taught by professors from institutions like Caltech and MIT, bringing a world-class education to any screen with an internet connection. These aren't dry lectures, they are immersive experiences featuring video lessons, interactive problem sets, and vibrant discussion forums where learners from across the globe can debate the nature of dark matter or help each other through the mathematics of general relativity. For those who prefer a more structured path, textbooks remain foundational, but even they have evolved. Many are now paired with online portals offering video tutorials, simulation software, and augmented reality features that let you project a spinning galaxy onto your kitchen table, examining its structure from every angle. This multi-sensory approach caters to different learning styles, ensuring that a concept that might seem abstract in text becomes vividly clear through interactive exploration. Perhaps the most impactful shift has been toward hands-on, experiential learning that makes grand cosmic concepts tangible. You don't need a billion-dollar telescope to understand how gravity bends light. A simple wine glass, a laser pointer, and a dark room can become a powerful demonstration. The curved glass base acts as a gravitational lens, bending the laser beam and creating a distorted image on the wall. A perfect analogy for how a galaxy cluster warps the light from behind it. Educators and organizations like the Astronomical Society of the Pacific have developed entire curricula around such low-cost, high-impact activities designed for use in schools, museums, and community centers. These projects prove that profound understanding isn't reserved for those with access to advanced technology. It sparks from creativity, curiosity, and the simple act of trying something for yourself. This philosophy is crucial for cultivating the next generation of scientists, engineers, and informed citizens, showing them that the universe is not a distant abstraction, but a dynamic system they can actively explore and question. The future of astrophysics education is already taking shape through breathtakingly innovative tools that promise to dissolve the remaining barriers between the learner and the cosmos. Virtual and augmented reality are poised to create the ultimate classroom, a fully immersive, interactive universe. Imagine donning a headset and not just learning about gravitational lensing, but actually reaching out with your hands to warp a virtual space-time grid, watching as light rays curve around your fingers, and then flying through a scale model of the Einstein Cross to see the multiple quasar images from every angle. This technology can transport students onto the virtual surface of Mars to interpret geological formations, or inside a particle accelerator, to witness the fundamental forces of nature. Furthermore, the open data movement is revolutionizing access, allowing students to analyze real, raw data from professional telescopes using cloud-based tools and simplified software interfaces. A high school student can now measure the light curve of a distant star, identify an exoplanet transit, or even contribute to classifying potential gravitational lenses in galaxy surveys, moving from a passive consumer of knowledge to an active participant in the scientific process, blurring the line between learning and genuine discovery. One of the most persistent myths about gravitational lensing is the idea that it's merely a trick of the light, an optical illusion created by our telescopes. This misconception fundamentally misunderstands what's happening. An optical illusion, like a mirage on a hot road, is a local phenomenon where light is bent by varying air densities, creating a false image. Gravitational lensing is something entirely different and far more profound. It is not an illusion but a real, physical distortion of the path light travels through the universe, caused by the warping of spacetime itself by mass. The images we see, the arcs, the rings, the multiple copies of a single quasar are genuine. The light from those distant objects has physically traveled along those curved paths for billions of years. Calling it an illusion is like saying the bend in a river is an illusion because the water isn't flowing in a straight line. It misunderstands that the landscape itself is shaping the path. Another common area of confusion is the belief that this bending of light somehow violates the laws of physics, particularly the idea that light always travels in a straight line. In a flat, empty universe, that statement holds true, but Einstein's revolutionary insight was that the universe isn't a static stage, it's a dynamic fabric. Mass and energy tell spacetime how to curve, and spacetime tells light how to move. So, in a very real sense, light is traveling in a straight line. It's just that the space it's traveling through is itself curved. The path it follows, called a geodesic, is the straightest possible path through that warped geometry. It's a subtle but crucial distinction. The laws of physics are not being broken, they are being fully obeyed, revealing a universe far more intricate and wonderful than the simple, classical model of absolute space and time. Dispelling these myths is about more than just scientific accuracy. It's about building a public that is comfortable with the incredible realities of our cosmos. When people understand that gravitational lensing is a predicted, measurable, and repeatable phenomenon, it transforms from a magical oddity into a powerful tool for discovery. This clarity helps combat the spread of misinformation, whether it's from well-meaning but misunderstood articles or from more malicious sources seeking to discredit established science. Clear communication is our best defense. By using relatable analogies, stunning visualizations, and transparent explanations of the evidence, we can replace confusion with wonder and skepticism with informed curiosity. Beyond lensing, the field of astrophysics is ripe with other popular misconceptions that could benefit from the same clear-eyed debunking. For instance, many people picture a black hole as a cosmic vacuum cleaner, actively sucking in everything from across the galaxy. In reality, a black hole's gravity is only exceptionally powerful very close to its event horizon. At a distance, its gravitational pull is no different than that of a star of the same mass. You could replace our Sun with a black hole of equal mass, and the Earth's orbit would remain completely unchanged. We would simply freeze in the darkness. The terrifying, sucking force is a dramatic oversimplification. Another widespread myth is that the expansion of the universe means that everything is moving away from a central point, like fragments from an explosion. This isn't the case. There is no center. Space itself is stretching everywhere at once, meaning every galaxy is moving away from every other galaxy, like raisins in a rising loaf of bread. Correcting these ideas isn't about pointing out errors, but about opening doors to a deeper, more accurate, and ultimately more beautiful understanding of the universe we all call home. Behind the polished data and the triumphant press releases, the discovery of this hidden galaxy is at its heart a profoundly human story. It's a tale written not just in light, but in late nights, caffeinated debates, and the quiet persistence that defines the scientific endeavor. If you were to step into the control room or the late-night lab during the peak of this investigation, you wouldn't just see computers humming. You'd feel the palpable tension of a group of people on the verge of something extraordinary, wrestling with uncertainty and their own exhaustion. Dr. Emily Richards, a postdoctoral researcher on the team, recalls the moment the final model finally converged. It was 3 in the morning. Most of the building was empty. We'd been tweaking parameters for weeks, and the simulation kept failing to match the Hubble observation. We were about to call it a night, convinced we were chasing a ghost in the machine. Then one last tweak, a slight adjustment to the dark matter density profile of the suspected dwarf galaxy. We ran it again, and there it was. The simulated distortion pattern matched the real one perfectly. The room was silent for a full minute, and then it just erupted. It wasn't shouting, it was this collective exhale of awe and relief. In that moment, you forget all the failed attempts. You're just there, connected to this tiny, ancient galaxy billions of light years away, and you're the first person in history to know it's there. These narratives are the lifeblood of science, transforming it from a cold, impersonal process into a relatable human adventure. They reveal the essential role of collaboration, a force far more powerful than any single brilliant mind. The hidden galaxy wasn't found by one astronomer staring solo through a telescope eyepiece. It was uncovered by a diverse, international team of theorists, observers, data scientists, and instrumentation specialists. Each person brought a unique piece of the puzzle. The observer who first noted the anomalous distortion in the data might never have confirmed it without the modeler who could translate that hiccup into a mass estimate, or without the software engineer who optimized the code to run those thousands of simulations in a fraction of the time. Dr. Kenji Tanaka, the lead modeler on the project, emphasizes this point. We have this romantic image of the lone genius, but modern astrophysics simply doesn't work that way. My most important tool isn't my computer, it's the whiteboard in the common room. That's where the magic happens, where an observer's frustration with a noisy dataset meets a theorist's wild idea about dark matter substructure. We sketch, we argue, we erase, and we build understanding together, one messy equation at a time. The discovery belongs to all of us equally. What personal lessons can we distill from these shared experiences? The first is a profound lesson in resilience. For every triumphant eureka, a moment that makes the headlines, there are months or even years of negative results, faulty equipment, and rejected proposals. The ability to endure that grind, to maintain curiosity in the face of repeated failure, is perhaps the most critical skill any researcher cultivates. It's a lesson in embracing the unknown rather than fearing it. These scientists are masters of living with ambiguity, of finding comfort in the questions themselves while they slowly, painstakingly work toward an answer. Furthermore, their stories teach us about the power of diverse perspectives. Breakthroughs rarely come from groups who all think the same way. They emerge from the creative friction between different disciplines, backgrounds, and ways of seeing a problem. An artist's eye for pattern might spot a lensing arc everyone else missed. A computer scientist's algorithm might reveal a correlation hidden in plain sight. This teaches us that solving grand challenges requires us to build bridges, to listen to voices outside our own expertise, and to value every contribution to a shared goal. Ultimately, the story of this hidden galaxy is a testament to the best of humanity, our boundless curiosity, our ability to work together across divides, and our stubborn refusal to believe that anything, not even an entire galaxy, can stay hidden forever. Sometimes the most effective way to grasp a mind-bending cosmic concept is to find its echo in our everyday world. We can think of gravitational lensing as nature's version of a simple glass lens, the kind you might find in a magnifying glass or a pair of eyeglasses. When light passes from air through the dense, curved glass of a lens, its path is bent, focusing the light to a point or magnifying an image. A gravitational lens operates on a remarkably similar principle, but instead of using shaped glass to bend the light, it uses the warped geometry of spacetime itself, curved by the immense mass of a galaxy or a cluster. The effect is the same. Light from a distant object is collected, focused, and amplified, giving us a clearer, brighter view of something that would otherwise be far too faint to see. This analogy works because it connects the utterly unfamiliar to the comfortably familiar, transforming an abstract relativistic effect into something we can literally hold in our hand. For a more dynamic comparison, we can look to the surface of a pond. Imagine dropping two pebbles into still water some distance apart. Each impact point creates a set of expanding circular waves. Now watch what happens when these two sets of waves meet. They don't just crash through each other, they interact, creating a complex interference pattern of ripples and troughs. If one set of waves is much larger and more powerful than the other, imagine a large rock and a tiny pebble. The smaller waves will be dramatically distorted and reshaped by the dominant pattern of the larger ones. This is a beautiful analog for weak gravitational lensing. The powerful gravitational field of a massive foreground galaxy cluster is like the large rock, creating the dominant warp in the fabric of spacetime. The light from countless faint background galaxies is like the gentle waves from the small pebble. As this light travels through the warped region, its path is subtly altered, not into multiple images, but into a coherent pattern of distorted shapes that we can measure to map the invisible mass causing the distortion. And for the most dramatic, strong lensing effects, the classic funhouse mirror provides a perfectly intuitive model. Walking through a hall of mirrors, you see your reflection stretched into elongated, towering figures, squeezed into comically short forms, or even duplicated and wrapped around a corner. This happens because the mirror's surface is not flat. It is deliberately curved and bent. Your light reflects off these bizarrely shaped surfaces and arrives at your eyes in a distorted way. Now scale this idea up to a cosmic level. The funhouse mirror is the warped spacetime around a massive galaxy cluster. The background galaxy is you standing in front of it. The multiple, stretched, and arc-like images of that galaxy we see are your distorted reflections, each one showing us a different path the light has taken around the cosmic curvature. This analogy brilliantly captures the weirdness and wonder of seeing the same object in multiple places at once, all due to the contours of an invisible landscape. The true power of these analogies lies not in their perfect accuracy after all. Spacetime isn't made of glass, water, or mirrors, but in their ability to act as conceptual bridges. They provide a sturdy mental scaffold upon which we can hang the complex mathematics of general relativity. They give our brains a way to feel the geometry of the universe, to develop an intuition for how mass and energy shape the stage upon which light performs. By starting with these tangible experiences, we can then more gracefully step into the deeper, more abstract truth that what we perceive as the force of gravity is actually the motion of objects following the curves of a flexible cosmic fabric. This process of finding earthly parallels for cosmic phenomena is a fundamental part of scientific communication, transforming the awe-inspiring from the incomprehensible into the wonderfully understandable. This revelation of a hidden galaxy nestled within another does more than just add a new pin to our cosmic map. It invites us into a much deeper conversation, one that has echoed through human thought for millennia. It forces us to confront the unsettling yet thrilling possibility that what we perceive as the complete, objective universe might only be a fraction of the whole story, a brilliant surface glow obscuring a far richer and more complex reality lurking just beneath. This is a moment that transcends astrophysics and taps into fundamental philosophy, challenging our most basic assumptions about perception, knowledge, and the very nature of what is real. We can trace this thread of thought all the way back to ancient Greece and Plato's famous allegory of the cave. He asked us to imagine prisoners chained since birth inside a dark cavern facing a wall. Behind them, a fire burns and people walk between the fire and the prisoners, casting shadows on the wall. For these prisoners, those flickering shadows are reality. It's all they have ever known. Plato's question was profound. If one prisoner were freed and turned to see the fire and the figures creating the shadows, and then was dragged out of the cave into the blinding sunlight to see the true world, what would he think? And if he returned to the cave to tell the others, would they believe him, or would they dismiss his descriptions of a brighter, more vivid world as madness? This 2,000-year-old thought experiment is a stunningly precise metaphor for our own scientific journey. For centuries, our unaided eyes were our chains, and the night sky was our wall of shadows. Every telescope we've built, from Galileo's simple spyglass to the mighty Hubble, and now Webb, has been an act of turning away from the wall and stepping further out of the cave. The discovery of a hidden galaxy through gravitational lensing isn't just a new shadow on the wall. It's a glimpse of the fire itself, a direct revelation that the sources of the shadows are far more complex and mysterious than we ever imagined from watching their projections. This leads us to a humbling and central question in the philosophy of science. How do we know what we don't know? The history of cosmology is in many ways a history of discovering the limits of our own perception. Every time we've built a new instrument that allows us to see in a new way, whether it's a radio telescope revealing the cold hydrogen gas between stars or an X-ray observatory spotting the scorching hot halos around galaxy clusters, we've uncovered a layer of the universe we didn't even know was missing. Before the invention of the telescope, the concept of another galaxy was unknowable. Before the theory of general relativity, the idea that gravity could bend light and act as a lens was unimaginable. Our ignorance was not a lack of effort, it was a fundamental limitation of our tools and our theories. The universe wasn't keeping secrets, we simply didn't know how to ask the right questions or in what language to listen for the answers. This hidden galaxy is a powerful reminder that our current map of reality, no matter how detailed it seems, is undoubtedly incomplete. There are unquestionably other phenomena, other forces, perhaps even other dimensions of existence that remain entirely outside our current conceptual framework, simply because we haven't yet developed the intellectual or technological sense to perceive them. This realization fosters a crucial humility, a necessary counterbalance to human arrogance. It is the understanding that our view of the cosmos is not a God's eye view, but a view from a very specific and very limited vantage point, a single planet orbiting a common star, using biological senses evolved for survival on Earth, augmented by technology that is still in its infancy on a cosmic timescale. The universe does not owe us easy comprehension. The fact that we have decoded as much as we have, from the life cycles of stars to the expansion of space-time, is a testament to human curiosity and ingenuity. But for every mystery we solve, a dozen new ones emerge, each more profound than the last. This isn't a failure, it's the very engine of science. The goal is not to arrive at a final, complete answer, but to continually refine our questions, to push deeper into the cave of ignorance with the unwavering faith that there is always more light to be found. The hidden galaxy is not an endpoint, it is a signpost pointing toward a future filled with even greater wonders and deeper mysteries, waiting for the next generation of thinkers to bring them into view. This spirit of global partnership is the very lifeblood of modern astronomy, transforming what would be isolated national projects into a truly unified human effort to comprehend the cosmos. The discovery of our hidden galaxy wasn't the product of a single nation's telescope or a solitary genius. It was a mosaic pieced together from data contributed by orbiting space observatories, ground-based telescopes on multiple continents, and analysis teams scattered across the world's time zones. This international framework is not merely convenient, it is essential. The universe operates on a timescale of billions of years and a physical scale of billions of light years, and no single country possesses the resources, the geographic diversity, or the monopoly on brilliant minds required to observe it fully on its own terms. By pooling our intellectual and technological capital, we effectively create a single, distributed global observatory that never sleeps, with instruments always pointed at the sky from somewhere on the planet, and with researchers always awake to analyze the incoming flood of data. Perhaps the most stunning example of this global potential is the Event Horizon Telescope project, which produced the first ever image of a black hole. To achieve the incredible resolution needed to see the shadow of a black hole at the center of the Messier 87 galaxy, astronomers needed a telescope virtually the size of the Earth itself. This was impossible to build, so they did something even more ingenious. They synchronized a global network of 8 existing radio telescopes, from the high deserts of Arizona to the frigid peaks of the South Pole, to all observe the same object at the exact same time. The data collected by each dish was so vast it couldn't be sent over the internet. It had to be physically shipped on hard drives to central processing centers where supercomputers correlated it. This Herculean effort, involving over 200 researchers from more than 60 institutions across 20 countries and territories, resulted in an image that captivated the entire world. It was a monumental achievement that would have been utterly impossible without deep, trusting international cooperation, proving that when we align our efforts toward a common, awe-inspiring goal, humanity can accomplish the seemingly unimaginable. These scientific partnerships do something profoundly important that extends far beyond the realm of astrophysics. They build bridges. In a world often fractured by political disputes and cultural misunderstandings, a shared scientific mission creates a neutral ground where collaboration is not just encouraged but required for success. When a researcher in Japan is waiting on data from a telescope in Chile to complete their model, or when a graduate student in India is working on code that will be used by a professor in France, national borders begin to blur. The common language becomes mathematics, and the shared goal is a deeper understanding of the universe. This creates lasting professional relationships and personal friendships that transcend the changing winds of international politics, fostering a sense of global citizenship and shared destiny. It's a powerful reminder that beneath our many differences, we are all inhabitants of the same small planet, looking up at the same stars with the same fundamental curiosity. Looking to the future, strengthening these vital partnerships will require intentional effort and innovation. We must continue to champion open data policies, ensuring that the incredible information gathered by publicly funded telescopes remains a global commons, freely accessible to any researcher anywhere in the world. We need to build more mechanisms for direct collaboration, especially with emerging scientific powerhouses and developing nations, ensuring that the next generation of astronomers is truly global and inclusive. This could involve creating more fellowship and exchange programs, hosting more international conferences in a hybrid format to increase accessibility, and developing even better tools for remote operation of telescopes so a scientist can conduct observations from halfway across the globe as if they were sitting in the control room. The future of cosmic discovery depends on our ability to not just continue these collaborations, but to deepen them, to weave an even tighter and more resilient global network of curiosity and wonder, forever united in the quest to unravel the mysteries hidden in the light. While we marvel at the cosmos through its grand gravitational lenses, the profound principles behind this phenomenon are quietly revolutionizing technology right here on Earth, reaching into fields far beyond astronomy. The core idea that mass can curve the path of light isn't just a cosmic curiosity. It's a fundamental insight that engineers and medical researchers are now harnessing to see our own world in astonishingly new ways. This is the beautiful, often unseen cycle of fundamental science. A discovery made to answer a deep question about the universe invariably spins off into practical applications that transform our daily lives. The study of how gravity bends light around galaxies has become a surprising but powerful muse for innovators designing the next generation of tools in medicine, materials science, and communications. In the realm of advanced imaging, the lessons from gravitational lensing are directly inspiring a new class of optical devices. Engineers are developing what are known as metamaterials, artificial substances engineered to have properties not found in nature. These materials are designed with intricate nanoscale structures that can bend electromagnetic waves, including visible light, in precisely controlled ways. Think of it as creating a fabric of space itself at a microscopic level. The goal is to build superlenses that can overcome the diffraction limit, a fundamental barrier that prevents conventional lenses from focusing light onto a spot smaller than its wavelength. This concept of using a carefully crafted structure to manipulate light paths beyond normal limits is a direct parallel to a massive galaxy acting as a natural superlens in space. While nature uses the warping of space-time, we're learning to use nanostructures to achieve a similar effect, potentially leading to microscopes powerful enough to watch individual biological molecules at work, or to lithography tools that can etch impossibly small circuits for next-generation computer chips. The impact is perhaps most profoundly felt in the field of medical imaging, where the drive is always to see deeper, clearer, and with less invasion. Techniques like magnetic resonance imaging and computed tomography scans rely on complex algorithms to reconstruct a three-dimensional picture of the inside of the body from a series of two-dimensional projections. The mathematical frameworks used to untangle the distorted light paths in a gravitational lensing image share a surprising kinship with the computational methods used to sharpen these medical images. Researchers are now adapting the sophisticated algorithms developed by astronomers to model how light bends around a galaxy cluster and applying them to enhance the resolution of MRI scans. These techniques can help to correct for distortions and blurring, effectively allowing a standard hospital scanner to produce crisper, more detailed images of soft tissues, tumors, or neural pathways in the brain, all without increasing the radiation dose or scan time for the patient. It's a perfect example of how a tool created to map the invisible dark matter of the cosmos is now helping to illuminate the hidden structures of the human body. The influence even extends to the burgeoning field of cloaking technology. While the popular idea of an invisibility cloak might seem like science fiction, researchers are making serious strides in creating materials that can redirect light around an object, effectively rendering it invisible to sight or undetectable to radar. The underlying principle again echoes gravitational lensing. If you can perfectly control the path of light, guiding it smoothly around an object like water flowing around a rock, you can hide that object from view. Current experimental cloaks use metamaterials to create this light-bending effect. Although we are far from cloaking spaceships, the same principles are being used to create radomes that can protect sensitive antennae from radar detection, or to design acoustic cloaks that can shield structures from the damaging vibrations of earthquakes by bending sound waves around them. The cosmic phenomenon of light bending has given us a blueprint for manipulating all kinds of waves for practical human benefit. Looking ahead, the potential applications born from lensing studies are limited only by our imagination. One tantalizing future technology could be the development of gravitational wave lenses. Just as matter lenses light, incredibly massive and dense objects could potentially lens the ripples in space-time known as gravitational waves. If we learn to detect and interpret this effect, it could give us a powerful new tool to study the properties of the merging black holes and neutron stars that create these waves, revealing details that are currently obscured. Closer to home, the continued refinement of metamaterials could lead to perfect optical lenses for our cameras and phones, completely free of any distortion or chromatic aberration. We might see the advent of revolutionary new solar concentrators that use light-bending principles to focus sunlight onto tiny, highly efficient solar cells, dramatically reducing the cost and space needed for solar energy generation. The fundamental research into how the universe bends light is not a closed chapter but an open book, and we are only just beginning to read the instructions it holds for building a brighter future. Beyond their profound scientific value, the warped and magnified images created by gravitational lensing possess an undeniable and breathtaking aesthetic power, a quality that has propelled them from the pages of astrophysical journals into the realm of art and popular culture. These are not the sterile data points of a research paper. They are cosmic masterpieces painted by the invisible hand of gravity itself. The most dramatic lenses produce ethereal Einstein rings, perfect luminous halos of light encircling a foreground galaxy, like a divine fingerprint smudged across the cosmos. Others create surreal, blue-hued arcs that stretch across the void like celestial smiles, or scatter multiple, shimmering images of a single quasar into a symmetric cross pattern that feels too perfect, too orderly, to be a random act of nature. For visual artists and photographers, these images are a boundless source of inspiration, offering a palette of forms and patterns that are at once alien and deeply harmonious, a visual representation of the underlying mathematical elegance that governs our universe. This intrinsic beauty is far more than a happy accident. It is a direct reflection of the profound elegance and simplicity of the physical laws at work. The same equations of general relativity that predict the bending of starlight also govern the graceful arc of a thrown ball and the stately orbit of our planet around the sun. There is a deep, satisfying unity in this. The stunning Einstein ring is not an exception to the rules, it is the rules expressed on a canvas of unimaginable scale. This connection between fundamental physics and sublime beauty creates a powerful bridge between the often separate worlds of science and art. It demonstrates that the pursuit of knowledge is not a cold, clinical dissection of nature, but a journey that can lead to objects of incredible splendor, where the logic of mathematics and the emotion of aesthetics converge into a single, awe-inspiring whole. Recognizing this powerful allure, museums and galleries worldwide have begun to feature these cosmic artworks in major exhibitions. Digital installations now transform entire rooms into immersive experiences, where visitors can walk through projected fields of warped galaxies, surrounded by the silent, majestic dance of light dictated by gravity. Renowned institutions like the Art Institute of Chicago or London's National Gallery have hosted shows where Hubble's lensing images hang alongside the works of the great masters, not as scientific documentation but as works of art in their own right, challenging viewers to consider where the boundary between empirical observation and creative expression truly lies. These displays do more than just beautify science. They contextualize it within the long human tradition of representing and contemplating the sublime, placing our modern, technological window onto the universe in a conversation with centuries of artistic wonder. The potential for deeper integration between these disciplines is vast and thrilling. Imagine a collaborative project between astrophysicists and kinetic sculptors, creating a physical installation where suspended masses of polished metal and glass literally warp a network of laser beams around them, creating a tangible, walk-in model of a gravitational lens that visitors can interact with and alter with their own movements. Planetarium shows could evolve from passive viewings into interactive performances, where a live composer and a visual artist react in real time to a data stream from an active telescope observation, translating the discovery of a new lensing event into an immediate symphony of sound and light. Universities could pioneer new hybrid degree programs that train science interpreters or data artists, individuals fluent in both the language of Python code and the principles of compositional design, whose entire career is dedicated to sculpting raw scientific data into emotionally resonant and intellectually accessible public experiences. By tearing down the artificial walls between the laboratory and the studio, we don't just make science more popular, we enrich our culture with a new vocabulary of form and a new source of meaning, reminding everyone that the drive to understand our universe and the drive to create beauty within it are, and always have been, two expressions of the very same human spirit. But of course, the most exciting questions are the ones we haven't even thought to ask yet. That's the real beauty of this entire endeavor. Every answer we find seems to open the door to 3 new mysteries. Your curiosity is the fuel that drives this channel and this entire field of discovery forward. So please share your questions and your thoughts in the comments below. What about gravitational lensing has you the most fascinated or completely baffled? Your inquiries might just become the centerpiece of a future video or a dedicated live session where we can dive even deeper together. This is a conversation, and we are all students of the cosmos, learning from the universe and from each other, one question at a time. From the initial spark of a theoretical prediction by Einstein to the breathtaking confirmation of a galaxy hidden within another, this journey through gravitational lensing reveals far more than a single cosmic secret. It illuminates the very process of discovery itself, a testament to the relentless human drive to look beyond the obvious and question what lies just out of view. This breakthrough is a powerful reminder that our universe is layered with mysteries, each one waiting for the right combination of curiosity, technology, and collaboration to bring it into the light. The hidden galaxy is not an endpoint. It is a beacon, guiding us toward a future filled with even more profound revelations about the dark matter scaffolding our cosmos, the violent dance of galaxy formation, and the fundamental laws that have shaped everything from the largest structures to the smallest particles. As we stand on the precipice of this new era of exploration, with revolutionary instruments like the James Webb Space Telescope and the Vera-C, Rubin Observatory coming online, the potential for discovery feels truly limitless. These are not just bigger telescopes, they are entirely new classes of observatory that will transform gravitational lensing from a specialized tool into a standard way of viewing the universe, allowing us to conduct a grand census of the hidden cosmos. We are moving from studying individual marvels to understanding the broader population of dark matter halos, faint dwarf galaxies, and even rogue planets that have eluded our detection. The questions we can ask now are bolder than ever before. Could we use lensing to map the detailed structure of an exoplanet's atmosphere in a distant star system? Might we even find evidence of physics beyond Einstein's theory by studying how light bends around the most massive structures in the universe? The answers are out there, written in the warped light of distant stars, waiting for us to learn how to read them. This ongoing quest is a collective human achievement, built by the countless researchers, engineers, and even citizen scientists who contribute their passion and intellect to piecing together the cosmic puzzle. It is a story that belongs to all of us, a shared narrative of curiosity and wonder that transcends borders and backgrounds. If this journey through space's deepest mysteries has sparked your imagination, then our mission here is accomplished. Your engagement fuels this adventure. Let us know in the comments which cosmic mystery you want to explore together next, whether it's the enigma of dark energy, the violent lives of black holes, or the search for life beyond Earth. Be sure to like this video and subscribe to the channel so you don't miss our next deep dive into the wonders of the universe. Thank you for watching, and never